1.1 Which of the following best illustrates balanced forces? So let's break that down before we even attempt to answer the question. When you're thinking about balanced forces, you're thinking F net is equals to MA and F net is equals to 0. Your object is stationary or it is moving at a constant velocity. That's when we can say that forces acting on an object, they are balanced. Let's look at option A. A person lifting a heavy object from the ground. Obviously, if you're lifting the object from the ground, the forces are not balanced, right? And then B, a big rock free falling to the ground. If it is free falling, there's only gravity acting on the object. Acceleration is not equals to 0. So we cannot say that the forces are balanced. And then C, a light stationary object. The object is stationary. So obviously our acceleration is equals to 0 meters per second squared. That is exactly what we're looking for. So the answer to 1.1, we can go with C. Let's look at 1.2. An 8 kg box is placed on a rough surface as shown below. If a force of 16.5 Newton is applied to the box and it accelerates at 1.5 meters per second squared to the right, the frictional force between the 8 kg box and the surface is, so again, back to the basics, F net is equals to MA. Let's sketch a free body diagram for the object real quick. So we just have the force that is applied, which is equals to 16.5 newtons, and we have some frictional force, which is what we're looking for. So if we substitute that into F net, we're going to say force applied minus frictional force is equals to MA. The force that is pulling the object minus all the forces that are opposing the motion. So that is 16.5 minus frictional force, which is equals to the mass. The mass is 8 kgs and the acceleration is 1.5. So 16.5 minus frictional force is equals to 8 multiplied by 1.5. That's supposed to give you 12. So you can see now that the frictional force will be equals to 4.5 newtons. That is because 16.5 minus something to give you 12. So that something must be 4.5 newtons, right? So that seems like our answer to 1.2 is actually B. Let's move to 1.3. 1.3, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it is dropped. Ignore all the effects of friction. In relation to the velocity time graph for the bouncing ball shown above, which statement below is correct? And then A is saying down is taken as positive direction. So let's look at that. Our ball is being dropped from a certain height and it starts going down. So if down was taken as positive, then our VT graph should immediately go up, but then it is immediately going up. So we're taking up as positive and down as negative, right? So option A that says down is taken as positive, we know that it is already not correct. Let's look at B. B says down is taken as positive. Again, we know that B cannot be correct because we can easily see that down is not taken as positive. Let's look at C. Down is taken as negative. Right. Now there's something to think about. Down is taken as negative and the ball is at its highest point of its bounce at C. So let's go and look at C. C is right here. C is right here. And we know fully well that at the highest point, V equals to 0 meters per second. So C cannot be our highest point because velocity is not equals to 0 at that point. Now by elimination, our only answer remaining is D. Let's look at it and see why it makes sense. Down is taken as negative, true, and the ball is at its highest position of its bounce at D. Yes, D can be our highest point because velocity at that instance, it is equals to 0 meters per second. Right, let's move to 1.4. So we have 1.4. Two identical solid spheres, each with a mass m and traveling at a speed v, move towards each other in an isolated system. The spheres have a head-on elastic collision. Which statement is correct for the collision as described above? So if collision is elastic, then the momentum EP before shall be equals to EP after, right? And then another thing that is true about an elastic collision, EK before should be equals to EK after, right? So the momentum before, because we have M multiplied by V plus M multiplied by minus V, because the other sphere, the other solid sphere, has the same mass but in the opposite direction. The momentum before is equals to 0, right? So the momentum after should also be equals to 0. Let's look at the kinetic energy. The kinetic energy before is a half M V squared plus a half M minus V squared, which is just going to give us, this will give us a half mv squared plus a half mv squared. So this is just mv squared. This is the kinetic energy before and the kinetic energy after. This is the momentum before and the momentum after. Let's look at our options. Option A is saying the spheres stick together on impact. We're not really sure. And then B says, let me not say A here because it seems like I'm saying A is the answer. And B says the total kinetic energy after impact is mv squared. Yes, that's what we have. The total kinetic energy before and after is mv squared. So 1.4, we don't even have to go through the other options. Our answer is B. We have proved that beyond reasonable doubt. 1.5, the mechanical energy of a moving object will remain constant if its free body diagram looks like this. If this is the free body diagram of the object, then the mechanical energy will remain constant. It will be conserved, so to say. So A, there are frictional forces present. If there are frictional forces, your free body diagram will not look like this. And then there is only gravitational force acting on it. We don't have to go any further. The answer is B. Mechanical energy is conserved when your free body diagram looks like this. Right. 1.6. A train is moving at a constant velocity of 10 meters per second while sounding its whistle, which has a frequency of 500 Hz. Take the speed of sound in air as 340 meters per second. What frequency will be heard by a man sitting in the train? So when the man is sitting on the train, the man and the train have the same velocity, right? So let me just do the math real quick. So we know that FL is equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. So V is the same for the man and the train. And then VL and VS, they are the same for the man and the train. So basically we have FL being equals to FS. So the man is going to experience the same frequency that the train is emitting because he and the train are moving at the same velocity. So 1.6, we have the answer being A. He will experience a frequency of 500 Hz, the same frequency that is being emitted by our train. 1.7, the diagram below shows a point P at a distance R from a charged sphere Q. Right, the electric field strength at point P is, let's look at A, directly proportional to R. No. It's supposed to be inversely proportional to R squared, right? Because E is equals to Q1 divided by R squared. So it's supposed to be inversely proportional to R squared, not directly proportional to R. So A is definitely not correct. Let's look at B, directly proportional to the square. So if it says directly proportional to the distance between the two, then it is incorrect. It's supposed to be inversely. And then C, inversely proportional to the square of R and to the right. And then D, inversely proportional to the square of R and to the left. Right, so now we just need to look at whether it is to the right or to the left. It is indeed inversely proportional to the square of R, as we can see from our formula. So now we have to be asking ourselves, Q is negatively charged. Where do the field lines point on a negative charged sphere? They point towards itself. The field line will point towards the charge itself. So you can see here that at P, the field lines will be pointing to the left. They will be pointing towards Q, right? So the answer here to 1.7 is supposed to be the field lines at P will be pointing to the left. They will be pointing towards Q, as you can see from the field lines that surrounds Q as a negatively charged sphere. So inversely proportional to the square of R and to the left. That is option D. 1.8. 1.8 is saying which of the following statements about the AC generator is true. The minimum potential difference produced is not 0 volts. It is 0 volts. So that cannot be our answer. B, the EMF produced decreases as the number of windings increases. That is not true. That is not true. We know from grade 11 that if you want to increase the EMF induced, you can increase the number of turns. You can increase the number of windings. So B cannot be correct. The maximum value of the AC can be increased by increasing the period of rotation. Well, I was initially conflicted between C and D. And then I realized that increasing the period of rotation is decreasing the time it takes for one cycle to be completed. Because period is the time it takes to complete one cycle. So if you increase the period, it means that you are now rotating very slowly. And that cannot increase the EMF. So by elimination, it seems like our answer is D. It also makes sense. The maximum value of the AC produced can be increased by increasing the speed of rotation of the coil. So 1.8 is our correct answer. Let's look at 1.9. 1.9 says that a battery with internal resistance is connected to a fixed resistor R. A voltmeter is connected across the battery as in diagram A. The battery is replaced by one with the same EMF but with a larger internal resistance as shown in the diagram. In diagram B, how will the voltmeter reading and current through the fixed resistor change compared to diagram A when switch S is closed? So EMF is equals to V external plus the current multiplied by the internal resistance. The EMF is staying the same. Our battery still have the same EMF, but then now it has more internal resistance. So let's look at what is going to happen. If you increase the internal resistance, the total resistance of the circuit is going to increase, and then the current is going to decrease. If the current is going to decrease and the external resistance of the circuit is still the same, then V external will also decrease, because R is remaining the same, the external resistance of the circuit. So let's look at what we have. A, with regards to the voltmeter reading, is saying that the voltmeter reading is going to decrease. Yes, the voltmeter reading is going to decrease, even though the EMF is the same. They're saying that switch S is closed. When switch S is closed, current is flowing in our circuit. So the voltmeter connected across the ends of our battery will be reading V external and no longer EMF. You need to realize that. So we're looking for answers with a voltmeter reading that is saying decreases and decreases. So now our answer can only be A or B. Let's look at the current through resistor. We have already deduced that the current will decrease, the current of the entire circuit, because it's all the same everywhere. In this instance, we don't have any resistors in parallel. So the current is also going to decrease. So that is option A. So our answer to 1.9 is A. And 1.10, this question actually doesn't make sense. The diagram below shows the kinetic energy versus frequency of a photocell that has a sodium metal cathode. The work function of sodium is 4.41 times 10 to the minus 19 joules. Let's just stay there. And then the question is saying the threshold frequency of sodium is, so we are given the work function, which is equal to Planck constant multiplied by threshold frequency. We have work function with Planck's constant. So the threshold frequency should just be work function divided by threshold, not threshold, but Planck's constant, right? And then I think, let me just look at the answer again. When you put that in your calculator, you're going to get 6.61 times 10 to the power 14. hertz. That is your answer when you use this information. And then we are given a graph. In our graph, the frequency where you start seeing some kinetic energy is given as threshold frequency is equals to 3 multiplied by 10 to the power 14 hertz, right? So on the same equation, we have two possible answers: 3 times 10 to the power 14 hertz and 6.61 times 10 to the power 14. Well, if you look at our option, we have 3 times 10 to the power 14 hertz as option B, right? Option C is in joules, so it cannot be correct. And option D is also in joules, so it cannot be correct. And then option A is also not correct, because our answer when we use the work function is 6.61 times 10 to the power 14 and not 4.41. Unless I'm missing something. I think we actually cannot answer this question. There is two possible answers. Only one is in the options provided. So if push comes to shove, you would have to choose the option that is there on your, or on one of your options. Please just let me know what you think about this question. Yeah, because I think it is very problematic.